Okay, so this talk will not be about waves, but about Oppenheimer-Snyder type collapse in the framework of the Einstein-Vlasov system. This is a joint work with Gerhard Rein, and this is a project I have been working on for a long time. And the motivation is as follows. So, as David pointed out, this solution by Oppenheimer-Snyder from 1939 has had an immense impact on general relativity since it predicts the existence of black holes. Now the matter model that Oppenheimer and Snyder used is dust, which is a very simplified matter model. It's a pressureless fluid. And moreover, the initial data they consider is just a homogeneous energy density, which they cut off at some radius. And the main aim of what I will talk about today is to show that this Oppenheimer-Snyder collapse can be realized by collapsing solutions of the Einstein-Vlasov system. And the Einstein-Vlasov system, the Vlasov matter is, in a sense, a more serious matter model than dust. I will come back to that, but that is one of the motivations today. There is another motivation for this project generally, and it has to do with a result by Christodoulou from 1984, where he shows that if you, instead of taking homogeneous initial data that Oppenheimer-Snyder took, but if you take inhomogeneous, or at least some particular class of inhomogeneous initial data, then you get what is called naked singularities. And so for those who are not acquainted with naked singularities, those violate what's called the cosmic censorship conjecture proposed by Roger Penrose. And basically this means that Einstein's theory will not be a deterministic theory in this that we would like it to be. So this is sort of serious. And the question is, of course, if those naked singularities which arise in dust should be taken seriously, and one aim with this project is to see if you instead approximate such solutions using Vlasov matter, if you can get rid of those naked singularities. That is another aim. And so let me just very briefly say something about Vlasov matter for those who have not studied this before. So this is a model from statistical physics, and you think of it as introduced by Boltzmann, maybe, not really, but he's one of the main figures here, and he used it to study a gas, neutral gas. So you have an ensemble of particles, which you describe by this density function on phase space, which now depends both on time, space, and momentum. And this model is used in many different situations in physics. So also when you study plasmas for tokamaks, for instance, they solve the Vlasov-Maxwell system. So in that case, the particles are charged like ions and electrons and so on. And you can also study the Vlasov-Poisson system in Newtonian gravity. And what we are concerned about here is the Einstein-Vlasov system. So you see that the particles in those situations are very different. So the particles, when you study the Einstein-Vlasov system, is typically stars or galaxies or even clusters of galaxies. And how you formulate the system mathematically is that you have density function now, you write as depending on time, and then space, and also 3 momentum here. And it should satisfy the Vlasov equation, where the index, when they have Greek index, they range from 0, 1, 2, 3. And this basically says, since it's 0 here, that the particles follow the geodesics of space-time. You see that you have a component P0, which you would like to express now in terms of PA. This you can do using the mass-shell relation. That is this relation. So, and where m now is the rest mass of each particle in your system. So we think of each particle having the same rest mass. And then you can define the energy momentum tensor using this expression. You see that you integrate over the momenta to get the different components of the energy momentum tensor. Then you couple this to the Einstein equations. I ignore the cosmological constant here because we're interested in isolated bodies. So then coupling those equations is the Einstein-Vlasov system. And one thing which is very nice with the system is that the definition of the energy momentum tensor implies that all energy conditions are satisfied automatically. There are some energy conditions in general relativity that you really would like to be satisfied, but for instance, if you're doing fluids, it's far from obvious that you can have a model which satisfies all those energy conditions. So this is the Einstein-Vlasov system. How is this related to dust? So if you now have a given space-time, you saw that the Christoffel symbols here in the Vlasov equation. Let's assume this is given, and then the Vlasov equation is just linear, and you can talk about distributional solutions. So if you now consider density functions of this type, where you see that you have a Dirac distribution in momentum space here. And this is a distribution, and it satisfies the Vlasov equation. And here you should think of the rho as the macroscopic density and the u as the forward velocity of your dust, because solutions of the Einstein-Vlasov system, where the phase space density have this form, is in one-to-one correspondence with dust solutions of the Einstein equations with density rho and forward velocity u alpha. So dust could be considered then as a singular case of matter described by the Vlasov equation. So this is the relation. So roughly what this talk will be about, you should think that when you want to approximate dust, you replace this Dirac delta with something which is almost a Dirac delta, but not quite. And to see that this has really an effect, let us just consider the Newtonian case first, because the same something about those matter models which really show that they are different is already captured at this level at Newtonian gravity. So if you take now the dust situation, that is the pressureless Euler-Poisson system in Newtonian gravity. So you have the density rho, the velocity field u, and the capital U is the potential which solves the Poisson equation. And then you can also consider the same situation, but using the Vlasov-Poisson system instead. You see that again you have the Poisson equation. Now this topic density rho is given by the integral of f over the velocity, and f should satisfy the Vlasov equation here. You can compare the solutions of those types of systems, and what happens is as follows. So for the dust system, the pressureless Euler equations, you can actually explicitly, almost explicitly, write down the solution, because if you now take a density having this form, where this is the characteristic function, this is the ball of radius r of t, here is r of t, and r of t should now solve this ordinary differential equation here. And if you now let the velocity field take this form, and you solve the Poisson equation, this form of the density, then the triple, rho u and capital U, is a solution of the Euler-Poisson system. And so this is almost explicit, but you have to solve this ordinary differential equation, but you can at least show that there is a capital T, such that when t approaches capital T, this r of t goes to 0. Capital T. So hence, the solution blows up. The density will be infinite. If you now compare to the situation for the Vlasov-Poisson system instead, then you can rely on those celebrated global existence results that were obtained about 3 decades ago by Pfaffelmoser and Lyons and Pertin. where they show that whatever initial data you take, the solution will exist globally in time. So therefore, you cannot have this blow-up scenario that we saw for the fluid. So, but you can, of course, consider and see what happens in the case of Vlasov matter. And my colleague then, Gerhard Rein, together with his student, Taggart, proved this theorem in 2016 that you can sort of prescribe initial data with a very, you should think of C1 now to be a small number. So even if you start with a density which is small, then you can construct initial data that at some later time you can make it very large. So basically you approximate what happens in the dust case, arbitrary well if you like, but you do not create this kind of singular behavior. So you should think of this basically as follows, that in the dust case, if you put particles at rest initially, and for instance on a sphere, and you evolve, they will all, because they are sitting at rest initially, and they follow the same evolution equations, so at the finite time they will all reach the center at the same time, and you will get infinite density. When you approximate with Vlasov instead, the particles are not completely at rest. There is some kind of dispersion. They move a little bit. So when you evolve, they will not enter the center at the same time, which will sort of avoid this blow-up scenario. So this is what happens in the case of in the Newtonian case. I mean, all solutions in the Newtonian case are global in time. If we now go back to the general relativistic framework, as I've already mentioned, this Oppenheimer-Snyder solution has really had a lot of impact in this field. I think it motivated also Penrose for his conjectures on cosmic censorship and so on. but that is for the homogeneous case. But there is also a lot of results about those naked singularities, as I mentioned, and it's a community that really consider them a lot, write a lot of papers. So I just, for curiosity, looked at archive and put in naked singularity as search word, and you see that you get very recent papers where they consider those naked singularities for dust. So I just took an example here. And the question is, of course, then, should the results about dust collapse in general relativity be taken seriously? And this refers to both, I would say, the Oppenheimer-Snyder collapse and those naked singularities. Because as we will see, also those Oppenheimer-Snyder solutions are not really what we want, actually. Because we will see that independently of how small initial data you take, you will always form a black hole. That is not really what you would like. So let me just review a little bit of this dust collapse. Generally, not only the Oppenheimer-Snyder solution now, but generally, and explain why this dust solution has been so important. And the reason is that you can solve it in a semi-explicit way. So what people do, they always, not always, but almost always, use comoving coordinates to describe this collapse scenario. And those coordinates take the metric then written in those coordinates, take the following form. So you have metric coefficient lambda, and you have the capital R, which is also metric coefficient. They depend now on time and radius R. You have some boundary conditions to make sure you have an asymptotic flat space-time, and you would like a regular center, which gives this condition. And if you now look at the dust system here, the Einstein dust system, then you should solve the Euler equations, coupled to the Einstein equations, where the energy momentum tensor is now given by this expression. In those comoving coordinates, you have the following feature that if you now start with initially your for velocity having this form, then the Christoffel symbols in this metric, they have this feature that many of those components are 0. And if you look at this equation 1, the Euler equation, it means that this will be the case that not only initially U has this form, but also at later times. So this means that the energy momentum tensor would be very simple in this case. You only have the T naught component that we call the energy density. The other ones will be zero. And the continuity equation now takes this form. And if you write out the Einstein equations, they look like this. And you see on the right-hand side now, where you have the energy momentum tensor, this is the only surviving component. Those are zero. The Einstein-Vlasov system, they will not be zero here. And you can then prescribe initial data for this system. So you prescribe some initial profile of the density and some initial data for this capital R. I call the time derivative here V ring. And if you have prescribed such data, you can define this quantity, the mass, enclosed within radius R, so to speak. And you can also define this quantity in terms of this data here, only initial data on the right-hand side. And if you have done that, you obtain the following equation for this capital R. That is what we call the master equation for dust. You see, here is the R, here is the R. The other guys here are given from initial data. If you can solve this equation, then it turns out that you can also write down the expressions for the metric lambda in this way, and you obtain an expression for the energy density having this form. It depends on this function capital R. And this holds generally for dust, not only for Oppenheimer-Snyder. So you can also do this for inhomogeneous data, etc. So, and exactly as in the Newtonian case, when you study this master equation, this can actually be solved by means of special functions. And then you can get some information, and that is that there is a function, T naught, which now depends on R, such that this capital R goes to 0 as T goes to this T naught of R. T naught of R is the coordinate time by which the dust particle, which started out initially at R, has reached the center. So the solution blows up at this time. And another quantity which is important when you are interested in formation of black holes and so on is the time when a trapped surface forms. And the general condition for a trapped surface in the given coordinates is that along all radial null geodesics, take the derivative along the parameter here, tau, then this should always decrease in this way. So this means that you get the relation. This quantity, which if you write things out, is nothing else than this condition, that 2m over r should be greater than 1. Where r now is this big function r. So if you now consider the special case of the Oppenheimer-Snyder solution, so for the Oppenheimer-Snyder, they took a special initial data. First of all, this W, as I said, depend only on initial data. They take to be 1, and they take the initial data for the density profile to just be a constant amplitude, cut off at radius 1. And then you can actually solve explicitly those equations. Remember this master equation, it's not you solve it normally by means of some special functions. In this case, you can actually solve it explicitly. And it turns out that this metric function R takes this form, where I have denoted this function, which only now depends on time, by gamma of t. It will play some role later on. And you see here that your density now will be this amplitude c of your density divided by this gamma function cubed. So, and this gamma you see will be 0 at a certain time, which is this time. Therefore, the density will blow up. You see, in this specific case of Oppenheimer-Snyder, then this blow up time, which generally depends on R, does not depend on R. It's just a constant. Here is this time when a trapped surface forms. We can also compute this explicitly. In this case, you get black holes, you get no naked singularities, and things are fine. And then you see one feature of this solution is that the dust solutions, they blow up in finite time independently of the amplitude C here. So if the amplitude is taken very small, the blow up occurs later, but still after finite time. You can think of the Einstein dust system to be as an unstable system, because whatever initial data you pose, however small it is, you will end up having a black hole. This is not really what you would like of a matter model, as far as my gut feeling tells me, right? If I start with something very, very dilute, you don't want black holes to form. And so then you can ask, what is the relation to Vlasov matter here? Because for Vlasov matter, you know that if you take very small initial data, then you will have dispersion and no black holes. And those results were shown first in the case of spherical symmetry by Gerhard Rein and Alan Rendell, 92, and then independently in the general case by Lindblad, who's here, and Taylor, and Davis is also here with Jeremy Chaudieu and Smulevici, and in the general case. So we know that that the situation for Vlasov matter is drastically different than the case of dust. So here you really, for small initial data, you have dispersion, you get no black holes. So how can you explain this now when we try to approximate dust with Vlasov matter? So the point is basically as follows, that you would like to take when you approximate dust, you take initial data of this type, right? Where this H now is an approximating Dirac distribution. So you can think of it as the amplitude of this guy is roughly like 1 over epsilon. And here you have the density, which we saw from the Oppenheimer-Snyder, was just an amplitude C, and then cut off as radius 1. And then, so basically we have two parameters here. We have the epsilon in this function, and we have the C determining the amplitude of the macroscopic density. So, of course, now if we fix the amplitude of the macroscopic density and then let epsilon go to 0 so that we approximate dust extremely well, so to speak, then the amplitude of F will actually to infinity. So, and therefore, those stability results by, for instance, Lindblad and David here, they will not hold, right? Because they require that F is small. If we do the opposite, we first decide how well we want to approximate dust. So we decide for some epsilon. And then we let the macroscopic density be very, very small. Then, of course, my F, the amplitude of F, will also be small. In that case, those stability results will hold. So, but this is a fundamental difference between dust and Vlasov matter. Okay, so now let me go to a little bit more technical things here. So when I started this project many years ago with Gerhard Rein, we tried to use those comoving coordinates because all dust papers almost use those coordinates, right? And literally, of course, you cannot speak about comoving coordinates for Vlasov particles because they move rather complex way, but you can, of course, just write down the metric as is the case for comoving coordinates and derive the system. And we wrote a lengthy draft where we thought that we had everything under control, but then we realized that we can actually not prove local existence. We had an issue at r equal to 0, and I believe you cannot prove it. That is what I believe. I cannot prove that I cannot prove it, but I also discussed with Olivier Sarbach, who is a person who knows a lot about dust and so on, and he is also aware about this problem also in dust when r is equal to 0. Anyhow, so we really were quite depressed in some sense because we had spent a lot of time on this. But then we found in the literature that you can actually use some other coordinates and still describe dust collapse in a rather explicit form. And those coordinates are referred to as Painlevé-Gullstrand coordinates. And they were introduced independently by Painlevé, 1921, and by Gullstrand, 1922. And as I said, in those coordinates, you can also derive, similar to what I showed you in comoving coordinates, some semi-explicit way to describe dust. What's interesting about those people, I have looked up a little bit information about them. So Paul Painlevé is a French mathematician who I don't know so much about. But Gullstrand is a Swedish, I would say, scientist maybe, who caught my interest in some way, because there are several things that I find interesting about him. First of all, he was born in the south of Sweden, but then in his education, he went to high school in a town called Jönköping, and that is exactly where I grew up, so maybe we have been at the same high school. It's possible. Another thing, what is interesting, is that he really liked math, but his father was a doctor of medicine, and he really wanted his son to study medicine, and this was actually quite successful, because Gullstrand did receive the Nobel Prize in Medicine, 1911. But he wanted to do math, and so on, right? So the interesting thing, 1911, the same year he got this Nobel Prize in Medicine, he was also elected to the Academy of Science for Physics in Sweden. And they have a lot of influence about the Nobel Prize and so on. And interestingly, if you know the story about the Nobel Prize in 1921, no Nobel Prize was handed out that year. Only the year after, the Nobel Prize was handed out for the 1921. That was to Albert Einstein, but for the photoelectric effect. And the reason is Gullstrand, because they wanted really to give Albert Einstein the Nobel Prize for general relativity in 1921. But one person did not believe in this theory, who was in the committee, and that was Gullstrand. He refused. The interesting thing is that 1 year later, he published this paper, right, in general relativity. And that year, they decided to give Albert Einstein the prize, but not for general relativity. But I don't know exactly what he was so concerned about, but as we all know, when you introduce new coordinates, things can become a little bit weird in some sense. So I can imagine that he was thinking about those things and was sort of not really sure what was going on. I don't know, but I found it interesting. Okay, so let me now say a little bit about the system in those Painlevé-Gullstrand coordinates. So in this case, you have, instead of those comoving coordinates, which they were diagonal, here you have a cross term. So you have dt, dr here. Geometric functions now are a and beta. They depend on time and radius, and you have some boundary conditions. And if you write down the equations, those are not all the equations, but those are the first order Einstein equations. So they take this form, where now rho, p, and j are matter terms, which are eventually given by integrals of f. I will show you in a minute. As always, when you do Einstein equations, you have too many equations, and you have to reduce to some reduced system. And it's sort of not, there's no one telling you which system you should take, right? So you have to really try to find a good combination here. And before saying exactly which combination we took, let me just say how those matter terms are related to the energy momentum tensor. So typically called the energy density. This is the current J, and this is the radial pressure, and they are related as follows to the energy momentum component, energy momentum tensor components. There's also another matter term, which is the tangential pressure, which did not show up in those Einstein equations, at least not the ones I showed you. It will play an essential role later on, so I keep it here. Another thing that is, when you study this kind of local existence and so on, in spherical symmetry, there's always an issue about r equal to 0, so it's convenient to use Cartesian coordinates, so that is what we use. And we also introduce certain non-canonical momentum variables, so that is basically a frame here. And in this frame, this p0 component takes this form, just 1 plus v squared. So this is the rest. You remember that you had a rest mass of the particles. This is this 1 here. And we denote this by this expression here. So then you end up having a reduced system. So this is the Vlasov equation. And we have picked those two of the first order Einstein equations. You see here is the tangential pressure, here is the current. In this function A, you also have the energy density. So A is given by this form. And those P and J and rho now, so rho entered here, they are in turn given by integrals of F in this way. And I have also kept the tangential pressure, even if it did not show up in this system. So if you now, this system, together with the boundary conditions, now constitute the reduced Einstein-Vlasov system in those Painlevé-Gullstrand coordinates. Of course, once we have a solution to this system, we want to see that all Einstein equations are satisfied, and that is, we are able to do that. Always a little bit tricky, I find it, but anyway, so this is the case. We prescribe some initial data, and there will be some issues about regularity here, but so I'm just saying we have some regularity conditions here, and some conditions at the center and so on. There is sort of a non-trivial thing here, is that this A ring, remember that A was given by this form here, depending on rho and J and so on, and beta, and it must satisfy this condition. It's in some sense a priori not obvious that you can find initial data of this type, but you can see that if you specify an F which is even in V, for instance, then the current J will be 0, so that you can find initial data which this works. Anyhow, so what we are able to do is to prove a local existence theorem of the following type. So you take this kind of initial data, and you can then show that the solution exists on some time interval where you have some regularity of the solutions. I have not specified the regularity because it takes a full page in some sense there. But basically, those regularity properties that we specified initially hold, but a little bit more subtle. But in particular, there is a continuation criterion, right? So, because you know, generally for Einstein equations, you have, for instance, in this case with Einstein-Vlasov, already Choquet-Briard a long time ago derived local existence, but as far as I know, I cannot really use that in a good way, because even if you maybe can get a local solution, you don't know any condition when you can extend it, right? So we, I think, really have to do this hard work in a specific coordinate system to get a solution to know what the continuation criterion is. And I would say that local existence is I think, harder than you expect in some sense. So let me show some tricky things here which enter into this proof. So you, of course, now set up iteration scheme, right, for your in order to obtain this kind of local existence. And then you have some issues about regularity. And the thing is that if you not sort of, if you know something about the regularity here, you would like to know, to take derivatives of the characteristics. So those are the characteristic solutions of the characteristic system. And so they contain first order derivatives. And so when you now take the derivative of this guy, then derivatives of those will show up. And then you need that beta are sort of C2, for instance, A and beta. And this is not obvious from the Einstein equations, as we can see as follows. So if you remember one thing about those equations is the following, that see this equation here, you have the beta function, and you sort of, the direction derivative here contains beta itself, right? So this is, and on the right-hand side, you see that I have the pressure term here. If you just now take a simplified form here, write u for beta and b for this part here, you obtain what I showed you here. Because we had an issue that we thought that at some point this is not possible, right? We were in this kind of situation that also in Painlevé-Gullstrand we will fail to get local existence. So then I suggested that we could just try to take a very simple case here. Assume that instead of beta, we just give a constant here. If you now have an equation of this type, where the right-hand side now you should think of as the pressure term, then you can solve this explicitly, so to speak, in this way. You now take the derivative of u with respect to r. It will hit in here, but you would like u to be c2. You would like to take another derivative. Then it will hit again here, but you only know that p is c1. So that seems to be a problem, right? So the question is if you can get some regularity from some other place of this term. And it turns out that the Vlasov equation is the rescue here. So if you also, for the Vlasov equation, make this cheating to replace this beta by b, which was now just a constant, then you can integrate the Vlasov equation in time. And what you then obtain for this bad term, so to speak, is that it is equal to J, which is the current, but this is sort of C1, and then you get another term here, but I have collected sort of the good terms in Q, so they are harmless. So this thing here, when you integrate in time, it had actually better regularity properties also in R. So of course, generally, when you cannot assume that this beta is constant, right, it is the solution, but so generally, you get many other terms when you do this, but the key mechanism that makes this regularity problem work out is due to this mechanism. Another thing concerning local existence, so this, what I just showed you, was specific for the Painlevé-Gullstrand situation. I mean, we have done local existence in other coordinates before, but that particular part had not shown up as a difficulty. This thing, though, yeah. Pardon me, if I take... I don't know. Yeah, I cannot say without looking at the equation, yeah. Another thing that typically shows up as a problem in local existence, it goes in this little community under the name of the magic lemma. And the story behind this is actually as follows. So the first sort of local existence proof for the Einstein-Vlasov system was done by Gerhard Rein and Alan Rendell in the 90s, and they published their paper in the Communicational Mathematical Physics. But when it was published, they received a letter from a former PhD student of Choquet-Bras called Francis Cagnac. And a story about him is that when he finished his PhD, he said that he wanted to continue with mathematics, but at the same time be a priest. And they organized this, so he got a position in Cameroon, where he was a priest and a mathematician. Therefore, nowadays there is a group in Cameroon doing Einstein equations and actually, in particular, Einstein-Vlasov system. Anyway, he pointed out that there is an error in this local existence theorem by Alan Rendell and Gerhard Rein. And they were able to cure this and wrote an erratum. And the result of this sort of what they cured resulted in this kind of what now goes under the name of the magic lemma. There's nothing magic with it, but it's sort of a trick you need to do. And the point is as follows. Again, if you consider those characteristics, right, they are solutions to this characteristic system. And you would like to sort of take now the derivatives with respect to t, x, and v of those guys and evolve. So what you really want to do is you want to say something about this guy and about this guy. But if you sort of look at the evolution equations for this and this one, it doesn't form a good system. But if you now add instead of considering just this guy and this guy, you consider this guy and this eta, which is a sort of modified version of this. You add a sort of non-trivial term here. And if you do that, then it turns out that the evolution equations for psi and eta become nice in the sense that you have a linear system here. And the coefficients that you obtain here, C1, C2, and C3, and C4, they are continuous and uniformly bound, you can show in N. But it also holds now for this C star N. And the reason is that, so this is a coefficient that looks not nice. It contains a lot of second-order derivatives and so on. But thanks to this way to set this up, it turns out that the C and star, the second-order derivatives, can be replaced by using these Einstein equations, which I have not showed you, the second-order Einstein equations, the G22 component. You see there are combinations of second-order derivatives, but they are equal to the tangential pressure, which you know has more regularity, so to speak. You can replace the second-order derivatives using this equation, and then you can also obtain similar information about this coefficient. So, but basically, we are able then to derive this local existence. As I said, it's a rather lengthy proof in the end, but this we have typed up at least. And then the sort of main result, in some sense, we are still not typed up. We are working on that at the moment, but I think I'm dare to say that this works now. And what we can show, so you can think of, now we want to control those solutions all the way up to the singularity, right? You can think of it in some sense as isn't continuous dependence on initial data sufficient to do this? But the problem is that dust is a singular case of Vlasov matters. You cannot rely on such results. So in order to control the solutions of the Einstein-Vlasov system, we have really to work sort of quite hard in the sense, and we're able to sort of control the solutions up to any time arbitrarily close to the singularity, and we can control it sort of as close as we wish in the uniform norm. And this result then, I find it interesting in the sense that it actually improves previous results on formation of black hole for the Einstein-Vlasov system. And in addition, it shows that this Oppenheimer-Snyder collapse can be taken seriously. I say at least for large data, right? As I said before, you have this issue about Oppenheimer-Snyder that whatever small initial data you take, you get the black hole, and that is, I don't really like that, but yes, I mean, in most situations when you can apply that result, you can do the same for Vlasov. So that is the consequence, and just some words about what goes on here is that, as I have indicated before, you take initial data where you have some kind of see that the momenta here is allowed only to be up to epsilon size, v squared. If it's larger than epsilon, then this function will be 0. And so you start out with particles almost at rest, but not quite. And in order then to control solutions of the Einstein-Vlasov system, we do that with a bootstrap argument, and we have really to control the solutions of this characteristic system very carefully. There is basically no room for flexibility here, then you fail. One consequence of our proof is that we get a homogeneous core. So that means that the solution sort of not very far out, because far out, remember that in dust you have this cutoff, right? For Vlasov you cannot do this cutoff, so you have a smooth transition to vacuum. But except for that small piece, you get kind of homogeneous core, and this is that it coincides with a homogeneous solution of the Einstein-Vlasov system. And that such homogeneous solution exists is sort of not obvious, right? So, and they will play an important role for this naked singularity stuff that I will say a few words about. So let me just say that you can obtain homogeneous solutions to the Einstein-Vlasov system by the following procedure. So if you now take function h, given having this property, then if I put up f, take this form, where now w is the radial component of the momentum, and L is the square of the angular momentum. So you have sort of new notation for the momentum variables, more adapted to spherical symmetry here. But I need to do this split because it's sort of not symmetric. So I put the function gamma in front of my w. And then this function gamma, my capital R, will be given by this expression, and my lambda, which is the other metric coefficient, will be given by this. The question is what gamma is. And I will show you what gamma is. But first, before doing that, I say that the matter components you can now write as follows. So the energy density takes this form in terms of this gamma. You integrate with eta, but you have this gamma here. I call this whole thing for phi almost. And the pressure is given by a similar expression, call that psi. And I can actually relate the tangential pressure, it takes this form, but it's not so important here. And then if you now, the equation that gamma must satisfy is this differential equation, takes this form where phi is this expression, psi is this expression. But this is closely related to this master equation for dust, actually. But what is important, what I want to show this expression is that if you look at the energy density here, and if you move out gamma from the square root here, you will get one factor gamma up here, and you will get 2 pi divided by gamma cubed. So this means that then you can compare with dust. So remember that this Oppenheimer-Snyder solution I showed you, then the dust density blowed up as, so this is just constant, and then this is gamma cubed, okay? And if you now look at how a homogeneous solution to the Einstein-Vlasov system looks like in terms of this gamma function, so this was the dust gamma. This is not exactly the dust gamma, but this should solve this equation I just showed you. Then you get this expression. And you see here, so again you get this 1 over gamma cubed, exactly as for dust. For dust, in this square root, this thing here is 0. You have no momenta, no contribution from momenta. So the initial momenta, as I showed you before, is of size epsilon. Okay? But you see that an eta goes from 0 to 1, but this means that this part here will give a lot of contribution when gamma gets close to the singularity, right? Gamma goes to 0. So eventually, gamma will sort of be much smaller than this epsilon, and then you will get a lot of contribution from the motion of the particles. So in dust, you don't have this piece at all. So the energy density for the Einstein-Vlasov system will look very different to the energy density of dust close to the singularity. And the energy density contributes to the mass function. And remember how the formation of trapped surface, the condition for that one, that is that 2m over r should be greater than 1. So the density contributes to m, which would then mean that this 2m over r will sort of more early become larger than 1 than for dust. So there is at least a mechanism which gives you sort of that you can believe that those naked singularities that form for dust may go away for Vlasov. We are not able to prove that yet. We have some arguments, but this is still an open thing. But let me finish just with some pictures from a numerical study. So together with Gerhard Rein, we have developed a code using the particle cell method to try to sort of evolve those equations that I showed you, but we have never really been having time to dive into this because of those analytic problems we have had, so we have not made any priority of that. But I have recently put a master student to try to understand this, and let me show some results. That you should take them with a big grain of salt. They are very new, and I'm not completely certain about them, but anyway, let me just finish with this. So again, as I mentioned, if you take inhomogeneous data for dust, you will get naked singularities, not for all inhomogeneous data, but for a certain class. And this, as I said, Christodoulos has shown this, but Erdely and Smar, already in 1979, did a numerical investigation about this. So they sort of give you explicit data which you can try, right? And so my master student, Edwin Martinsson, had studied those Erdely-Smar initial data, but for the Vlasov. And those Erdely-Smar, so now you see, if you now translate those into expression in this Painlevé-Gullstrand, the initial density becomes a bit ugly here, but what you should have in mind is that the Erdely-Smar initial data, they have two parameters, p and zeta. Here we choose p equal to 3/2 because then we can solve a certain equation. So then we only have one parameter left, and that is this zeta. And then you see that your initial density is not homogeneous. It's not just a constant. It takes this form. If you really look what happens for small zeta, then it's almost homogeneous. But there is now a critical, this parameter zeta is such that if it's above roughly 7.5, then you will have naked singularities. And this you can see from the following picture. So this is dust, right? So take now dust with this zeta less than its critical value. What you see here is that you send out null geodesics, like this. And, and here is the singularity. So if you send out a null geodesic here, very, very close to the singularity, you want it to be trapped by, you want it to be caught by a trapped surface, right? So that is what happens in this picture here. And this is exactly when below this critical parameter. But for dust, if you're above this, so for instance, if you take zeta to be 7.6, then you see that if you send out a null geodesic very close to the singularity, it will escape to infinity. So that will be the violation of cosmic censorship. Now you do the same data for Einstein-Vlasov, but again, take it with a grain of salt here. I'm completely convinced. But so first you take this case which was below the critical value, and then you get the singularity here, and this is capture. I mean, it hits the trapped surface, as in the dust case. And then you take the supercritical case, and then also in that case, you send out an null geodesic close to the singularity, and in contrast to dust now, this hits the trapped surface. But again, take this with a grain of salt. We have to do a careful investigation here. But at least there is some indication that Vlasov matter may dissolve those naked singularities, although I am not sure. Okay, so I think I stop here. Thank you very much.